So welcome to the second lecture on parallel and distributed computing in the summer term 25. So today there will be a few more definitions of terms, in particular in the classification of multiple instruction, multiple data computers, and we'll have some basics on networks, and then we talk about the scaling laws. This is what I wanted to do today in the lecture. So, starting with classification of parallel computers, say we have some parallel system. So the most basic distinction is, according to Flint's nomenclature, there is this SIMD machine, single instruction, multiple data. This is something that was popular kind of a bit in the 80s. Then it became less popular, and now it's becoming more popular again because this is where we do artificial intelligence stuff. So it began in the end of the 2000s when graphics cards were coming up. This again gained some momentum. What was in between and still is important is multiple instruction, multiple data. This is where most of what we consider computers, what you have in front of you, what I have in front of me here, are kind of part of. Yes, but there is now further distinction into what you probably don't have in front of you, namely distributed. Memory machines, and as we started to discuss last time, the programming model that we use in distributed memory machines is different from what we have when we use shared memory machines. So concerning the shared memory machines, we have already said that there is these uniform memory access, which we call UMA. Then there is something we have not yet mentioned. There is COMA, cache-only memory access. Then we have non-uniform memory access. Actually, this is now very very common. So memory access time depends on where things are stored in memory, and there we have already mentioned the cache coherent NUMA and the non-cache coherent NUMA. And then in the distributed memory world, we have something that's called massively parallel processor. We have something that's called network of workstations. I think that now is a good, because this is something that you can do now because you always have networks, so you always have workstations, so you can put them together and say we can do this now. And then we have what we're also going to use, our cluster here, and I mean, it's a good thing that you have this lecture here this time, because we are going to, this cluster is potentially turned off next year, and it's not clear whether we get any access to the next cluster, because the cluster that we buy now is for research purposes, not for teaching. Yeah, so it is a good thing that you take the lecture now, because I don't know whether we'll have the same lecture, whether we can actually do the same lecture with the same exercise next year. This year we have access to a cluster. As you can imagine now, this cluster is also pretty old in principle, but the new ones are just faster. Yeah, they work the same way. Okay, let's just write down these names. So MPP is massively parallel processor. So usually this is a specialized system with a unified operating system. Okay, so it could be that this machine was built for, these machines are built for a specific purpose, yeah? That you want to solve something very, very specific. I mean, there are machines that always do the same thing. Think about the weather forecast also, right? Yeah, so there's actually a machine built for that purpose. So depending on what you're going to do, you're probably not getting in touch with these machines. Then network of workstations. So this is the stuff that you have in front of you now. Network of workstations. So you could say this is a loosely connected group of individual computers. Maybe if we are running out of loosely connected group of individual computers with a, say, standard, Ethernet or something, the standard network. Okay, so say you are distributing your workload over these computers somehow, and they will connect via some network to themselves. So hopefully, if you do it right, the message would go from one computer to the other and would not go through Australia. Yeah, but this could, in principle, also happen when they are just connected over the internet. Yeah. So, but this network is not necessarily extremely fast. So it's the network cards that are in this computer actually for the internet. Yes, sending stuff very far around. So the machines that we call cluster are similar but different. So here we have a network of computers usually relatively simple computers. So for example, they may not have, or they usually don't have their own disk. Yeah, there's only compute nodes. And here there is an emphasis on high performance network. Usually these things are also physically close together, so that there's a physical short path between these computers, and in each of these nodes we have a separate instance of the operating system, but it's usually a very slim operating system compared to what we have in the network of workstations. So, I mean, one thing that you could say, for example, is that workstations, they are kind of assumed to be somewhere in the outside world. Yeah. So when part of the hardware that may not be the fastest on Earth, there's also some software layers in between. For example, here we insist that everything is encrypted that is sent out, yeah, between workstations, because they can easily be attacked from outside. So in your network of workstations, so the messages that you send around, they will be typically being encrypted, which of course is a lot of overhead. So if you are in a cluster, then the assumption is that the protection is somewhere from the outside, and the messaging in between the compute nodes is not encrypted. Yeah, so they are faster also from the software perspective. So, for example, here my laptop is everything has to be encrypted. I was, for example, traveling to Tunisia, and before I was allowed to go into Africa, I had to encrypt everything. Otherwise, they don't allow me in. They don't allow me out. Okay, yes, the other names that we already had, CC, NUMA is cache coherent non-uniform memory access. Then we had this NCC, NUMA. This is non-CC, okay, non-cache coherent, I mean, NUMA. And then we have COMA. Cache only memory access. It obviously sounds like a disease, right? Okay, COMA, NUMA. So kind of a little bit of difference. So NUMA machine would kind of look like this. So what we have is we have here our cache. The cache is connected to our processor. And then we have a memory. The memory has always some directory, so that the cache actually knows where things are in the memory. And if now two machines talk to each other, then what happens is that the datum is taken from the other memory. But the memory, or the memory of the other machine or of the other node, but the datum has a fixed home position. Yeah? Therefore, because there is a fixed home position, if you have to access the memory of your neighbor and you work on the memory of your neighbor, it will take usually a longer time than if you work with your own memory. This is why this is non-uniform. This, compared to coma, so coma is a bit more complicated. So in addition to a directory where you find this, you could say, what's the difference between a directory and a tag? You could say this is a two-level index. Yeah. So there. Okay, let me draw the other picture. So there again is a cache, a processor, directory, and tag saying where we put things, and what we do is that when the datum is used, the datum migrates to where it is needed. Okay, so then we have to have an additional directory because we also have to see where it has moved to. And this is, so we get several indices that we have to take care of. So now there is, in a sense, there is more overhead when things are moving around, and you have a more indirect addressing, but then it is in the machine where it's actually used. Okay, so far the classification. Let's go briefly to the networks. So in computer science, so you're not, anybody studied computer science here? No. Then you don't get to this lecture. You have your own. So networks is, okay, what is network? A network is the connection, or the network here is understood as the connection between compute facilities, so, or not facilities, compute nodes, yeah? And we'll have here in this, we write this node, this dot here will be the compute node. So this is any machine that can do any computation. And then in between we have a connection in what in graph theory we call an edge. So, and then we draw our network like this. So we have nodes, these are the computers, and in between there are these connections, meaning that this computer here can talk to this computer, but for example, this computer here could not talk to that computer. Yeah? So in reality, of course, it can talk to this computer, but it has to talk to this computer in multi-step way. Like you don't, you are in the internet, you don't have your cable to YouTube, even though that may sometimes be useful to have this direct link. No, you have you have many possible ways to get to the same resource. Actually, this is the idea behind the internet, because the internet, the reason why the internet was introduced, so not web pages, but the network behind the internet. This is actually was introduced to have a fail-safe communication network in the case of a nuclear war. Yeah. So the idea is that information search is, that you have a dense network and information searches its own way through the network. Yeah, and because you have many possible ways, so if an atomic bomb drops somewhere, it simply goes the other way around. So I mean, like the entirety of the inner United States would be devastated. Yeah. So then there would be still a cable from, say, New York to San Francisco going over Australia the other way around. Yeah. And it would the message would automatically find this way. So, but here we are not so much interested in the internet, but in fast networks that are used to let computers that we want to work together. Work together. So for this, we have to introduce again a few terms. Say the distance between nodes. So distance between nodes is the shortest path in terms of the number of edges. So we are not talking about physical distance, even though physical distance matters. Yeah, but physical distance, actually the physical distance is the length of the cable. It's not, the distance of the computers. But what we count here is the steps, so the number of edges that we would have to that we would have to go through to actually get to a place. Yeah. So we come to the examples in a minute. So this is the distance. Then we have the degree. The degree is the largest number of edges at a node. So we say largest number because in a network not all nodes need to have the same number of edges attached to them. Yeah, so we look at the one that is largest. So for example, there are star networks, where a server is individually connected to say 20 computers. So each of these computers is only connected to the server and not to anything else, but still the degree of this network would be 20 because the computer or the node with the most connections has 20 connections. So that would be the degree, and then there is the diameter of a network. So this is the largest distance in the way that we define distance between any two nodes. So say this is the worst case connection. So how many steps you have to go to get to that particular machine. Okay, then let's look at some types. I've just said something about a star type network, but this is not on my list, I just recognize. So, obviously, you can have a fully connected network. So fully connected network, say we have 4 computers, then this would mean that any of them is connected to any other of them. So say we have n nodes. We will say we'll always have n nodes. Now this network would have what diameter, very obviously? Give me a number. No. I think it's okay. Now I see whether you are listening. 1. It has a diameter 1, because the furthest distance between any 2 nodes is 1, because they are all connected to each other. Yeah? So then what is the degree? Degree is n minus 1, yes. Because it's connected to n, to all the others, but not to itself. So it's n minus 1. And the number of connections this is now pretty large, is n minus 1 factorial. Okay, so then there is a linear, so this is all connected. Now this was the maximum. Now let's look at the minimum that we can do. The minimum that we can do is a linear connection. So say we have like four nodes in a row, and each of them is connected to their neighbors. We have n nodes. We have a diameter. What is the diameter of this? It's n minus 1. What is the degree? Yes, it's 2. I mean, we said we take the maximum, yeah. So this here has 1 connection, and that here would have 1 connection, but there are 2 of them that have 2 connections, yeah. So this is why the degree is 2. Yes. So the number of connections here, this is what we call what's this? Post-problem, Pfostenproblem. What's the English word for Pfostenproblem? Okay, Konstantin can tell us what it's called in Ukrainian. No, you can't. No. Why not? Can you tell me in Russian?
Just I heard this term in Germany.
Okay. So this is you have a fence, yeah, and there's the post in the fence, yeah. So this here, say this is the fence, and this here are the posts. So you have 1 post more than you have fence segments. So this here can be improved by connecting the last one in the row with the first one in the row, right? And then we get what we call either a ring or fence post error. Yeah, okay. Okay, the fence post error is when you do it wrong. So actually the fence post problem, then you still have the potential of solving it correctly. Okay. So ring 1D torus. So basically, what you do? Okay, I make it a little bit larger here. So you put everything in a ring. Now the diameter of this. What's the diameter of that? Yes, it's n by 2 because you always take the shorter, but it's the because this may not be divisible by 2. It's the lower bound, and the degree is obviously 2 because now all of them have 2 connections. The number now here, if you have a so if you have a fence that is closed, your fence post problem is you have the same number of fence segments as you have posts. So we have a 1D torus, then we have a DD torus, DD torus. I think a 2D torus I may be actually able to draw. Let me try. Okay, so important thing in a torus is using, you could say, a Cartesian interpretation. Or we only go. Okay, so there is no connection in this diagonal here. Yeah, so they are always, the connections are always along one dimension. So, but since they are torus, I have to connect this to this and this to this, and we would actually have to connect this here to this here, and in addition this here to this here. So this makes it a torus. The diameter of this is D. D is the number of dimensions. N is the number of nodes in this. So this is the D's root. Yeah, n by the power of n divided by d. This thing 1/2 because we can go both ways, and the lower bound of this. This is the diameter, and the degree. The degree is 2D. Number of connections is n times d. So then there is one important other network to consider, and this is I'm going to the next page. This is the d-dimensional hypercube that has n equals to 2 by the power of d nodes. You see, this is not very flexible concerning the number of participants, if you will. Yeah, so they have to be a power of 2. And in 3 dimensions, we can actually draw the hypercube, because hypercube in 3 dimensions is a cube. Yeah, so this would look like this. And here the advantage of this hypercube where each node is connected with d neighbors. So the dimension actually, maybe I'm writing this a little bit further away. So I've forgotten one connection here. So the number of dimensions is the number of connections that each node has. And here the positions, this is the beauty in this, the positions can be indexed by d bits. So say this is three-dimensional, so we have 3 bits. Yeah. So the first here would have 0, 0, 0. Yeah. Then say this would have 0, 0, 1. This here would have 0, 1, 0. And the one in the back would have 1, 0, 0. So then this here would have 1, 0, 1. This here would have 1, 1, 0. And this one here would have 1, 1, 1. So by knowing these indices, it is pretty easy to find a way through this network. Yeah? Because we can put our paths through this kind of network by changing one bit at a time. See, for example, we want to get from 0, 0, 0 to 1, 1, 1. Yeah? So there's no direct connection between them. And there are, of course, many ways to go there, yeah? But all of these ways basically look like this. We go to a neighbor. By going to a neighbor, we change one index. Then from there, we go to a neighbor of this by changing one more index. And then from this, we change one more index again, and we come here. So this means that the distance between the node where you start with and the node where you want to go to is always equal to the number of bits that are different in the index. Yeah? So number of bits different into data. There's actually a name for this. I don't know whether you, in your informatics studies, you may have heard this, in your computer science studies. Any idea? The distance between two data, between two values. Ever heard about Hamming distance? Yes? Yeah, so exactly this is the Hamming distance. Yeah, so the distance between nodes is the number of bits different in the index. This is what computer scientists call Hamming distance. This is the number of non-matching bits in two words of the same length. So the difference between data, the number of bits that are different. And the number of bits that are different, so the Hamming distance of the indices is the distance of the two nodes in the network. Therefore, we can actually write down the diameter of the network is exactly d, and this can also be written as the logarithm of the base 2 of n, and the same thing is true for the degree. It's also d, which of course again is the logarithm to base 2 of the number of nodes. Okay, so this was our short nomenclature about networks already. Yeah, so there will in the exam, this is always kind of a little bit of interest. In the exam, there will be a few short questions on networks. Yeah, here you can get your 5 points each. Let's come to the next part in now parallel execution or parallel. Okay, let's say we call it parallel speed up. So the reason why we do things in parallel, I mean, obviously compared to doing things in serial, is usually because we want to have the answer faster. Yeah, and otherwise we could do everything sequentially. And this has certain implications and limits that we have to take into consideration. So some limiting factors in parallel computing. So we cannot just split everything. I mean, like the thing you want to build a skyscraper, you cannot build the skyscraper in parallel everywhere because there need to be something in between where you put the second floor, yeah, or the fifth floor. So you have to somehow come from below, and once you have like a skeleton, you can actually do more things in parallel. Yeah. Yeah, so what are things that hinder us from doing everything just in parallel? There are, of course, data dependencies. Data dependencies means that something I want to do depends on something else that I have to do, and this forces us to use sequential execution. So this is the example that I had just for a minute. So when you want to build the third floor, then there must be a second floor or something in between that you can build the third floor on. Then you also have to start everything up. So this may also take some time. then you have what we call bottlenecks. This would be the access to, say, shared or slow resources. Yeah, then if you solve things in parallel, so if you do your homework and you build a group and you say you do this part and I do that part, then you also have to sit together and discuss how you get together with the information that you produce and the information that you need. Yeah, so this means you have to have communication. So communication is something that if you do everything yourself, you don't need. Yeah, so this is actually additional work that you have to do only because you're parallelizing things. Yes, and also you have to manage your resources. So everything, at the end, the managers are the ones are apparently very important because they get the most money. Yeah, but they don't do any work. They just say, so you do this work and you do that work, but this is very important because if it's not organized, I mean, if you try to do the homework in a group together and you don't get organized, then neither of you knows what part you should do and when it should be done. Okay, there are now two typical questions that we could ask. The first question is how much faster can a problem be solved on n cores instead of one core. So the one core being the serial version, yeah, and now you say we have more workers, n cores, so n workers, so how much faster do we do the work? So you would hope that this is my typical question that I always ask, because we are here in a civil engineering department. If one worker takes 1 hour to build a wall, how quick can 3,600 workers build the same wall? Yeah? So, what's your answer? It depends. Yeah, but certainly not, they won't, I mean, you put 3,000 people in one place, they don't build the wall in 1 second, right? So, okay. So how does it actually work? The problem I was just addressing is that the amount of work that we do stays the same. Yeah, we have a fixed amount of work and now we can attach more workers to it. Yeah? And this is, okay, I'm at the end of the page. This is what we call strong scaling. So when you do parallel computing, strong scaling is one of the things that you have to know. So what you do, scaling means you get more resources, yeah, you get more workers, more construction workers, more compute nodes, whatever. But the problem remains the same. So you're scaling up the resources, but not the problem. This is what we call strong scaling, because this is the difficult way, yeah? So you have one worker building a wall of 1 meter, and you want to see how can you solve the same problem with more construction workers. Yeah? So, meaning you have a worker and you have a problem. And in science, having a problem is always a good thing. In life, having problems is a bad thing, but in science, you won't have problems. So, what you do, this is your problem. So, the problem has a size, yeah? And now say we have worker 1 and worker 2. You split this thing up, and, okay, I estimate it, but the problem stays the same size. And say you have worker 1, worker 2, worker 3, worker 4. You split things. Okay, it's just an estimation. I think it's not exactly the same size that I draw, but you split up the work more and more and more. So, meaning constant problem size varying number of workers. So the workers are the cores. So what we are interested in is particular time. Time that it needs to solve the problem. And say this here, what we have here is the number of cores. And say we have one core. So if we have one core, now I need to have a different color. Then we have a part of the problem that can be parallelized. And I will go to call this part P. So this is the time of the parallelizable work. And if you don't get me, what I mean is the time that you need to do the parallel work in serial. Yeah, so the entire time that it, so the entire amount of hours that all your workers together would have to do. Yeah, and if it's only one worker, that this person would do all of this. So, and then on top of this, there is something that we call S, and that's the time of the work that you can not parallelize. So now the idea is, if you have two workers, then the parallelizable work would be split in half. No, not the work. The time that you needed would be split in half. The the work that is cannot be parallelized, this would stay the same. And on top of this comes something that you did not need to care about before, and this is the communication time. That now, since you have several people here, you have to communicate, yeah? So this is time for inter-process communication. So now when you make this larger, I mean, we assume that the real problem is finite. Yeah? So meaning, so you cannot make it necessarily infinite. Okay, we later make the assumption that we can go to infinity, but n say n is large. Yeah? So or should we? Okay, let's do it with infinity. Let's say we have infinitely many. Yeah. So if we have infinitely many workers, then the little bit inaccurate, crazy assumption is that the work that can be done in parallel takes no time. Yeah, because everybody is just doing something very quickly. Yeah, and so no time is needed. So there is no time for this. The non-parallelizable part is still there. And with regard to the communication, I'm now a little bit in trouble because I don't know how big I should draw this. But if you want to communicate between an infinite number of people, that could get pretty large. Actually, you could, or if you really do this, if you really have a problem that you want to split up into many, that you want to distribute over as many workers as possible, then this will actually be slower than if one does it alone, right? Pretty sure. So, what we observe is that, say, the number of cores. So say the number of cores goes up, then we see the parallel part is going down, the serial part stays the same, and the communication part goes up. This is our observation. So now in the simple theory that we now want to have a look at, the communication is usually ignored. I mean, there's also problems that don't require a lot of communication. But communication in general is difficult to estimate. So that simple models, and this is kind of also a problem, but simple models neglect it. But in reality, this can be a big part . Okay, I assume that you will see when you write your first parallel program that you make it, that you potentially make it slower by parallelizing it rather than doing it in serial, yeah? Due to this communication thing. Okay, now let's ignore communication and build some simple model with TS being the serial execution time and TP the parallel execution time. So then TS, what is TS, is simply the work that you can do in parallel, but you do in serial. Yeah? So it's all the work piled up together, plus the time for the serial work. And the parallel time is the serial time for the work plus the parallel time divided by n, with n is the number of cores. So, and then there is a law on how much speed up you can get of this. This is Amdahl's law. We are interested in the speed up, and we call the speed up S. And because we already used S, I write a very, now this is, the other one is supposed to be a small s, and this is supposed to be a large s. Speed up under strong scaling. So strong scaling is the thing where the problem size is the same and the resources are increased. So this speed up is defined as the time that we need to serially run the problem divided by the time that is needed when we run it in parallel. Now, if we put into this what we have here, so the serial time plus the parallel, the time of the serial part plus the parallel part, S plus parallel divided by n. So actually we are done here, but this is often not considered the most convenient way of writing these things down, because they all depend on the actual scale of the problem that you want to solve. Therefore, there is a different way of writing this down, namely with the fractions. So there is what we call a serial fraction, and the serial fraction is defined as the time that we need to solve the part of the problem that cannot be parallelized, so the serial part, divided by the entire problem, so S plus P. This is the entire problem. And this is the serial fraction. And then there's, of course, the parallel fraction, and the parallel fraction is the parallel part of the program divided by the entire work that has to be done. Yeah? So this is the parallel. Obviously, the parallel and the serial fraction together is 1. Yeah? This is the entire program. So we can rewrite the speed up in this way as being 1 over the serial fraction plus the parallel fraction divided by n, and this is also written as n times the serial fraction plus the parallel fraction. Okay, so now this is Amdahl's law, and now we look at the limit of this. So the question, if you have all the resources in the world, how fast can you solve your problem? Yeah? Or how much faster, what is the speed up? Yeah? So you need 1 hour now. I give you all the resources in the world. How quick do you have your answer then? This you get by taking the limit of n is going to infinity of n divided by n fs plus, so the serial fraction plus the parallel fraction, and this obviously becomes 1 over the serial fraction. Meaning that the speed up that you can reach is limited by the serial fraction of the workload. Meaning that your speed up is always smaller in print. So now you can discuss whether it's smaller or equal. So I would say that you will always produce some sort of communication, and this communication will even slow it further down. So it's pretty, so this is why I don't write equal, but there are some problems that don't require communication, and then you could, in principle, write equal, right? So, but, okay, but then also the parallel work will take non-zero time, even if it's distributed over many, many machines, yeah? So it will take at least 1 clock cycle. So, and therefore the speed up is always smaller than 1 over the serial fraction. Yeah, so when 10% of your program cannot be parallelized, then the maximal speed up that you can reach with infinite number of cores would be 10. Okay, so this is the strong scaling speed up. Any questions? If not, I'm a bit quick today, but doesn't matter because we have something else in a minute. Okay, if no questions, then I have the next question. How much more work can n cores do instead of 1? So now there's a different scaling that we call weak scaling. And this is when the problem size grows proportional to the number of workers. So now it's not the question to build one wall, 1 meter of wall, yeah, with one worker or with 3,600 workers. But if one worker needs 1 hour to build this 1 meter, so how much time need 3,600 workers to build 3,600 meter of wall? So this, yeah, looks like this. We have a worker, we have a problem size, and now we have worker 1 and worker 2, and our problem size has doubled. So this means for our time, for our serial time, this means we have the time for the serial part plus P. Now P is the work that is the original amount of work for one worker. So if we have more workers, then we also have more work to do. So then it's P times N. Yeah, because this is what we would do if everything would be in serial. And conversely, now TP is S plus P, because every worker has to do their serial part. Yeah, so serial part, so they have to put on their working clothes. Everybody has to do this themselves, and then they have their part of the wall that they have to build, and this is always the same 1 meter that they have to build. So this is not dependent on N. And for the speed up of this, there's a different law that's called Gustafsson's law. This gives us the speed up under weak scaling. We call this S again, and it's again the entire time for the serial execution divided by the time for the parallel execution. And now what has changed is that this is S plus P N divided by S plus P, and this is also the serial fraction plus the parallel fraction times N. Now, what is the speed up of this if you take the limit of N going to infinity S? So remember, there's no communication involved in this. The limit N to infinity of Fs plus Fp times N, this is obviously infinity. Yeah? So if you have a weak scaling problem, so you increase the amount of work that your workers have to do, then this can speed up your result indefinitely, so you can get to an infinite speed up. This is possible in weak scaling, but this is not possible in strong scaling. Okay, so any questions to strong or weak scaling? Because if this is not the case, then we could actually, do you need, okay, I'll turn off the recording and then let me